value of their neighbors. Scores accumulate on a digital ledger where high-ranking peers are monetarily rewarded with additional weight in the network. However, this form of peer ranking is not resistant to collusion, which could disrupt the accuracy of the mechanism. The solution is an incentive mechanism that maximally rewards honestly selected weights, making the system resistant to collusion of up to 50% of the network weight. The result is collectively run intelligence market that continually produces newly trained models and pays contributors who could create the information theoretic value. Okay, okay. Introduction. The production of machine intelligence has come to rely mostly entirely on a system of benchmarking where machine learning models are trained to perform well on narrowly defined supervised problems. While this system works well for pushing the performance on these specific problems, the mechanism is weak in situations where the introduction of markets would enable it to excel. For example, intelligence is increasingly becoming untethered from specific objectives and becoming a commodity that one, expensively mined from data, two, monetarily valuable, three, transferable, and four, generally useful. Measuring its production with supervised objectives does not directly reward the commodity itself and causes the field to converge towards narrow specialists. Moreover, these objectives do not have the resolution to reward niche or legacy systems. Thus, what is not currently state of the art is lost. Ultimately, the proliferation of diverse intelligence systems is limited by the need to train large monolithic models to succeed in a winner take all competition. Standalone engineers cannot directly monetize their work. And what results is centralization, where a small set of large corporations control access to the best artificial intelligence, like OpenAI. A new commodity needs a new type of market. This paper suggests a framework in which machine intelligence is measured by other intelligence systems. Models are ranked for informational production regardless of the subjective task or data set used to train them. By changing the basis against which machine intelligence is measured, the market can reward intelligence that is applicable to a much larger set of objectives. Legacy systems can be monetized for their unique value, and three, smaller diverse systems can find niches within a much higher resolution reward landscape. The solution is a network of computers that share representations continuously and asynchronously peer to peer across the internet. The constructed market uses a digital ledger to record ranks and to provide incentives to peers in a decentralized manner. The chain measures trust, making it difficult for peers to attain rewards without providing value to the majority. Researchers can directly monetize machine intelligence work, and consumers can directly purchase it. Interesting, dude. Interesting. Interesting. Okay, here's the tough part, bro. We begin with an abstract definition of intelligence, Hinton et al. In the form of parameterized function trained over a dataset d equals xy to minimize the loss. Our network is composed of n functions, peers, where each is holding 0 or more network weights s stake represent on a digital ledger. These functions together with losses in their proper proportion of stake represent a stake weighted machine learning objective. Our goal is the distribution of stake I as an incentive to peers who have helped minimize the loss objective, and importantly, in such a way that it is difficult for a small proportion of stake to collude as means to maximize their distribution in the network without minimizing the loss. In this paper, we suggest this can be achieved through peer ranking, where peers use the outputs as inputs to themselves and learn the weights, where peer I is responsible for setting the ith row through transactions on a digital ledger. Setting weights using an Fisher's information pruning score, LeCun et al. In the ranking calculation achieves an idealized scoring where each peer's incentive is equivalent to its pruning score, the cost and entropy induced by removing it from the network. However, this approach is not resistant to collusion where peers vote for themselves, notably instead of using and set weights to enhance their own inflation at the expense of the network. This attack is trivial since the digital ledger cannot audit the parameters of each model, only the intermodel weights, W. We extended the naive ranking method to evade collusion with an incentive function, which limits reward to peers that have not reached consensus in the network, assuming no group of peers holds more than the majority of stake in the system. Then peers can only attain inflation by working to attract votes from the majority, a core assumption in many decentralized systems like Bitcoin. Reintroducing our terms, our incentive mechanism requires a stake vector S and a set of weights W, where rows are inter-peer rankings. We also infer a trust matrix T from the weights, where T equals 1, and only if there is a non-zero edge between peer I and J. We define peers who have reached consensus as those with non-zero edges from more than 50% of the stake in the network. This is simply the normalized values. Hey, dickhead, get your mind right. Don't preach to me about my perky habit. This is my life. To ensure the mechanism is differentiable, we define this computation using the continuous sigmoid function. The sigmoid produces a threshold-like scaling that rewards connected peers and punishes the non-trusted. The steepness and threshold point can be modulated through a temperature Q and shift term X. Consensus function is this with temperature Q equals 10 and X equals 0.5. The activation takes the trust scores and produces an exponential scaling up to our inflection point where a peer is connected to the majority. We use consensus term to scale the original rankings. As peers attain more weight in the network, they increase their inflation exponentially up to 0.5. In section 10, we show how this ensures that the larger of two competing subgraphs comes to own an exponentially larger proportion of the network through inflation. My dog Kyler says, yo, imagine you have a BitTensor agent that can just go ahead and understand all this and optimize its performance. I turned that video into a project plan, Flash 2.0. I posted in the members chat. I appreciate you, bro. I'm gonna check that out here soon. This consensus described above protects against naive collusion by making it difficult for small groups to achieve inflation. However, it does not provide an incentive for correctly